And a little bit about myself. I'm originally a landscape designer and getting more and more interest in technologies. And since 3 years, I'm working as a consultant here in San Jose as well as in China for my former colleagues in Tsinghua University and related institutes, and teaching Civil 3D and Revit and especially how to combine different softwares, including other software like Alias and yeah, what comes around for Grasshopper, Rhino, of course. But we seeing now the possibility to going away from Grasshopper and Rhino for many tasks because we can use Dynamo for it. So before we start to dive into some live demos, I would like to give a short overview about what is generative design and why it is important or why it's maybe not important. And when we see there are some other buzzwords around this, like parametric design and computational design, and they're not all the same. They're quite similar. They have some many overlays, but if you look to the evolution of generative design, it starts with parametric design, what we actually all using in Civil 3D, because whenever you draw an alignment and you build a corridor and this profile and alignment, then you are working parametrically. Um, what That's the classic way of BIM modeling. What is important is that the algorithm, how this all is calculated, is not visible to you. You can't change on this one if you think you have a better algorithm for solving some of the problems, or even you have an algorithm for a problem that isn't solved yet in Civil 3D. So that's the where parametric design is limited. And so the next step is what we call computational design. So it's have also this all these parametric aspects, but you have now the chance to change the algorithm or introduce your own algorithm. That is very useful when you have a lot of repetitive tasks. Like usually you see in many lectures in the last years, how repetitive task in document production is done, or by doing objects along alignments in certain distance, like lamps and trees and things like this. And therefore is computational design very helpful. And that is actually the base of generative design, because for generative design, we want to have multiple design options. Their options are mostly created automatically or in a certain manner that you can compare them and evaluate them. And that started with the project Fractal, and it's emerged into the project Refinery, where you then extend this generation of many models with the evaluation by analyzing the models, by selecting a preferred option and using algorithmic learning in order to improve this solution. So like Autodesk give in his material a very nice definition about generative design, but we need to be careful. Uh, will be not the only solution for design. It's actually only useful for very specific tasks. So I don't believe that generative design is the overall new design paradigm what we have to live in the next years. I thinking that generative design is very useful for tasks or for evaluate models on measurable outcomes, like you can measure or you can predict carbon dioxide production or sequestration. You can calculate stormwater runoff. That's are things what you can calculate. Uh, that is one, but many things like aesthetic values we cannot calculate. We may can rank them in a certain manner. And the other one is that the opportunity to create many variations lead very quickly to an overwhelming amount of variations. And I think the right solution is that you have a guidance, because human beings are very strong in some very quick analysis where computer even take longer. We just look at it and we know it's right or it's not right. We don't need to analyze it deeper, because human beings have one capability what computer don't have. Computer can give answers, but computer can't ask questions. And asking the right question is the basic of a right answer. And this will be the human task. And so that's as a short overview. And I think we can now look into the option we have in Civil 3D for programming. And as I say, we're using basically Dynamo, and inside Dynamo, we're using the visual programming as well as design script, as well as Python, and as well as zero-touch nodes that is basically C# programs encapsulated. And if you see in this diagram that Dynamo is very easy to learn, that's why it's put it in a green. And it's very open, so you can see and learn from every sample you can get. It has some shortcomings when it comes to speed, and it is limited in its capabilities. So the next step, logical, and as will be also seen in my demonstration later, is to go to design script. Design script is the underlying programming language of Dynamo, and mostly every task what you can do in visual programming, you can simplify and describe shorter and more readable later in design script. My design script have some more capabilities when it comes to programming logic, what is very limited in visual programming. So creating loops and stuff like this, that is not the strength of visual programming. Visual programming is very based on a linear or multiple linear processes that end in one point, but it's not designed for looping. So if you have like iterations, you definitely will end up with design script. But design script have still a very good access to all the elements we need. So the access to especially the Dynamo elements, but also access to AutoCAD and Civil 3D elements is very easy in design script. When this is not enough, then it comes to Python. So Python is a full capable programming language. Design script, we will see this later when we are working in the demos where design script has its shortcomings, and there jumps in Python. Python is still an interpreter language, even you may compile it. So it means all the programming is visible to you and readable to you. So you also can learn a lot from samples, and you can see everything what is done. But with Python, you have the access to the whole Civil 3D and AutoCAD APIs. That means things that are not implemented in Dynamo and Design Script, you can implement by yourself in Python. That is very important because Civil 3D is very new to Dynamo. So many things are still missing, and that is where Python jumps in, and Python helps you to access these elements very deep, as much as AutoCAD is open in this API. So you can do almost everything with Python, but Python has some shortcomings in speed, because it's an interpreter language. And where it comes to really heavy calculating tasks, then it comes to zero-touch nodes. That's actually C#, like all or most of the plugins for Civil 3D are written in, and it's a very similar process than like writing plugins, but it is supplied to you as an DLL, so you don't see what is inside. So, or you see the source code maybe on GitHub, like for the zero-touch nodes I'm using. So this source code is open source and freely available, and everybody can read and understand it, and you may later see it on screen. And but C# is really good when it comes to heavy workloads that need to be handled and time consuming. So like if you will see later, the nodes for refinery, they are basically all zero-touch nodes in C#. So that is enough about the theoretical framework. So let's jump in to what we are talking about, the design task, and that it's our landforms. And landforms are quite beautiful, but also complicated. And their range goes from land art over the typical grading for landscape design to grading for engineering design. Like if you can see on the left-hand side, that is the Desert Brass project in Egypt from the Romanian art team. And in the middle, that is, as far I know, the first landscape design drawing using contour lines. It's a park in Paris, and it's created during the renovation of Paris under Haussmann. And on the right-hand side, you see contemporary approach to design of excavation and landfills with a more organic and natural, or what's called geomorphic approach to blend this design better into landscape, but also it's improves stability of slopes and water management on these landfills. That is also a task what is very intensive in computation. We focusing on our samples in landscape and in land art, because I'm a landscape designer, so there is my preference, and it's also where we can reduce the complexity of the project in a certain manner so that everybody can follow up with the tasks what we are doing. So let's start with the first demo, and it's about NURBS and ruled surface and their translation into Civil 3D thin surfaces. So let me now change my screen. I hope everybody can see it, the Civil 3D screen. And here we see a typical problem in landscape design. So the landscape designer pay a lot of attention about a nice, smooth, organic waveform grading. And on the end, of course, he's using NURBS or ruled surface for it. I think, let's check this one. Yeah, it's a ruled surface. And this one is actually a NURBS, also built from a ruled surface, but to show that it works with both, I already changed it. And then when we start grading this with Civil 3D, we ending up in something very unpleasant, I would say, solution. Like, let's see this surface on how it's graded traditionally. Let's turn it on. Let's see it as contours and triangle. And you can see it's very simplified. So I graded a little bit the flat part as part of the path design as a corridor, and then of course, I can now drop a couple of points onto the NURB surface, or I can get isolines from the NURB surface and put them as break lines into my thin surface. But this is hell a lot of work, and we often don't do it, or our engineering colleagues don't do it, and then the designers are getting upset, and maybe they are right on this. So what we can do about this is, putting in more points or putting in more break lines derived from the NURB surface. And that is as this is a repetitive task, this is really one of the strengths of Dynamo. So let's see how we can do this. So let's go and fire up Dynamo. I think it is already. Which Dynamo when it is this one? Let's close this. Yes. Come on. No. Okay, now we can open Dynamo. And with Dynamo, we're creating complete from scratch. So let's have a new node. And shortly, so you see on the left-hand side in the menu all the objects. What you need is this special package. That's a zero-touch node that I created, and that has the elements we need for getting from NURBS surfaces and ruled surfaces points. This is a function that you don't find in the out-of-the-box nodes coming from Dynamo, and if you need it, you just go to package, using the package manager, search for package, and then you search for ALC NURBS, and that's you download it, install it, and then you have these nodes ready. So that is really good, and Dynamo is really is on a good track now. A lot of people providing additional nodes. You can see there are a couple of them like Clockwork, and what is a very important one is this Civil 3D toolkit if you work with Civil 3D and Dynamo. So let's start. So the first thing what we need actually is getting our objects from AutoCAD, that's our AutoCAD objects, into our visual programming environment, into Dynamo. And this starts with AutoCAD selection and select objects, and we need two of them. So let's get two of these nodes. We already can select them, so then we go back. Well, there we are here. And sorry, let's turn off first our terrain, what we don't want to see. Change this to no display and get the NURBS layer back. Here we are. Now we go back to Dynamo. And now we can select this one, our ruled surface, and we can select our NURBS surface. And you see that the nodes are changed from yellow to gray. The yellow means there is some problem happened because there was no object selected. So what we see that this object is basically the ID, the database ID, what is coming out of it, and that we pushing into our special nodes for surfaces and NURBS. So let's get first, the upper one was the surface, get points. And then we just lacing them together. And you already can see here, we have some points that worked already. And we're getting the other points. Let's see, we're changing to seeing the and we can see that there are a couple of points, and they are derived from the on the node vectors of the NURB surface and the ruled surface, because they actually are parametric objects. So we are actually working in a parametric design. We are just not able to get these parameters directly over into Civil 3D. So if we want, we can increase the density of these points. So that is given in this two U division and V division. So when we want to increase this, let's say we double them. So what we need is an integer input. Okay, come on, integer. Number slider. Yeah, I can use a slider, that's fine. Okay, one is maybe enough. Having two in different directions also. So let's put in some sliders. And say instead of 1, 2, and in the other direction maybe even 3, and we're lacing them in. Let's check. And you can see immediately that the number of points is going quickly up and getting very dense. So I'm actually with 1, what is the standard value, good. So I don't need all this one. So we already have the points. So now we need to think about how we're getting these points into Civil 3D. So of course, we see there will, in the next demo, there are nodes to creating COCO points or blocks or something like this, what we can use as a surface definition. But I prefer for such complex objects to write them in first in a file, in a text file, and read the text file in. That's avoid some bigger problems when it comes to point numbers to COCO points. So if you manipulate COCO points directly out of Visual Basic and you close and you reopen, you may have some problems with the automatic point numbering in Civil 3D. So that's why my way for where I maybe change a little bit more, and I'm expecting some design changes, I have like a interim backup by writing all these points out first into a file and importing the file into Civil 3D. So how are we doing this? So what we need is a CSV file. So let's see how we get a CSV file. Export CSV, that sounds promising. Okay, what is this node asking for? So it's have no output. So you can see every node had on the left side an input, and on the right side an output, and void means no output will be provided by this node. But it have two inputs, so it seems it needs the data and it needs a file path. So the file path we quickly putting in by hand as a simple string. So let's use this one. Let's delete this one because we're recreating it. And we need to give a name, and the name is a surface, ruled surface. Comma separated values. And this name or this path we're hooking in here, and we try to hook in our points, and we will see that nothing happened. No, it happened. But when we open it, we will see this is not a point file how this one is needed. So it looks actually like this. New share. So this is not what we want, because we want to have really only the values. So we need to clean up this a little bit. Getting X, Y, Z out. We could do this in this text file, but why we should do this when we can do this correctly out of our Civil 3D node. Where is my, here. So here we again sharing our screen, and let's get from each point the X, Y, and Z value. So the node for this is point X, point Y, so point Z. And you can see that this here on the left hand denotes giving you a lot of hints, or plus means creating new nodes. This means you are changing them, and the question mark, of course, means you're getting values from them. So we have point X, point Z, and point Y, and we're hooking our point into here. And this one we just still taking off. And in order to see what happened, we're putting in a watch node. And we can see we have now a pure list of numbers. So now we need to put them together into a list, and we've separated by comma, and to putting values into a list, we're using a list command, and this is a list, and it seems we need the list create. There it is. That creates us a list. So these are the first element. This is the second element. And this is the third element. And now we see how this looks like. And it seems we have three lists, but they are not in the right order. So we need to pivot the whole list or transpose this whole list. So let's see what node we have for this. Transpose. And this is the structure how we want to have it. I would recommend it's not really needed in this case, but in many cases is you don't want to have a list in a list. So you want to have it as a one list. And that is sometime when you, in the next pro demo, we will see this more when you're working with list. And it's very important sometimes that you reduce the dimension of the list, and this command called list flatten. So let's put this one in here. No, sorry, between this one and this one, and let's rewire the nodes. and something went wrong because we flatten it too much. We only want to flatten the 1. So let's put an integer in there. Let's search it. It's in the input basic input, just input, just input. No. Basic input integers. Now we don't want to have a slider. We want to just having input. Then we do it just like this. We already start a little bit design script. There should be, it should be called number input, right? Number input. Basic number. Okay, let's try to find the number input for an integer. Let's just keep it on 1 here. Use levels. Okay, that's maybe even easier. Okay, level. Let's try to get it directly out. Let's see. And let's see what we got. We have now a ruled surface CSV. Let me share the screen for this one. Here we are. So this is a typical CSV file, how everybody know how he's getting from the surveyor, and that's are the points that's describing our ruled surface. So now we can go back to Civil 3D. And we can now create our new surface, what we call from NURBS definition point files. Sorry. And here we can now add point file, adding ruled surface CSV, and that's correct. And we see it's done, and it's replicate the NURBS surface quite well. So let's do the same for the other surface. Back to Dynamo. Here we are. Let's share this screen. And let's remove this package. I think that's good. And we're doing actually almost the same for the second one. So we can copy all these nodes. Copy. We moving them here, putting these points in. To this one. And giving this one other name. In this case, NURBS. I actually would recommend to change here to manual to control the run of the program, that you're not updating the files too often. Okay. And let's run it. And let's see what it has created. We have a second file called NURBS-CSV, and we can now get this one into our Civil 3D, add NURBS. That's all correct. And good. And now we can analyze this as a standard because this is a standard tin surface. So hello. So let's turn off the NURBS. I think we did a mistake in because we was overwriting the file by accident in Civil in Dynamo, because we had the same name for a short moment because we didn't have it on manual. So let's run again. So here's the Dynamo node, a little bit clean up. The flatten is not necessary. So just get it like this. So you can see, I just changed the destination of the files. There was some problem in the access to this folder. Now we can run this. Now we can see in this folder the two files, and we can see in our Civil 3D file how we add these two files to our surface. So let's create a new surface, call it from NURBS or just NURBS. Add as definition the 2 point files. Okay, now here we are. And these are can be analyzed like every other tin surface in Civil 3D for sloping. That is, in this kind of gradings, the most difficult things to do. So let's do this quickly. Let's do a quick slope analysis. Okay, and change the style to elevation bending, slope bending 3D. Okay, and you can see you can do all this analysis what you are usually do in Civil 3D, and you can say to the designer that is too steep and this is too much. What I would like to mention, what you can see here is a stair that is created by the plugin that's also available. It's a stair, or what you can get on the AppExchange from Autodesk, and it's called LX Stair, and it's a parametric staircase for Civil 3D. Is it installed? Home. It isn't. Okay, it was on the other computer. So good. So now we come to the next demo. The next demo is we recreating the artwork of the Desert Breath, because there we had a lot of repetitive tasks, and there we using Cogo points directly in Civil 3D and created in Dynamo. So what we are doing is we starting with a complete empty drawing, matrix, because Dynamo works in matrix. So there are nodes for changing units to imperial, but basically Dynamo works as a matrix tool. That is sometimes quite difficult in Revit, because Revit works internally with inches. Okay, does it open? And we're going into our Dynamo, and here we're also starting very simple. So what we need is from scratch, what we need is from the Civil 3D, civil objects, Cogo points. And we want to create a Cogo block derived from the Dynamo geometry. So putting in this node. So in this case, we're working the graph backwards. Working backwards the graph is the logic that Dynamo is also using. So Dynamo is not, design script is not per se an imperative language. So there is no given order how Dynamo is, or you don't have so much control how Dynamo is executing. So it's evaluate the graph from the back, and then it pulls the information in what is needed. And we're doing actually the same. So we need a geometry. This geometry is a point. So let's create a point by coordinates. And it's need to know where this point goes. It should go in the current document. So Dynamo is in the moment only able to handle one document in one window. So you can't go to other drawing from Dynamo directly. So that's why you need to close always Dynamo and reopen it after you change, if you want to change a drawing. So let's see, we need to get the current document. Here it is. And we can define a layer by a string, or we can say we just put it on the current layer. Is the node for this one layer? Oh, name. Let's go into the tuning. Let's search in Autodesk, AutoCAD, documents, get the current layer. So it is need to know from which document, and then we get a name of this layer out, and that we can hook in here. Do we see already something in here? Let's go here. Yes, so it's already created one Cogo point for us. Coming that the point coordinates has a standard value 0, 0, 0 for x, y, z. So we have done all what is needed. So we may want to give the COGO point description. So we may later, if we want to work with COGO point groups, that we can sort them. So they say that is from get a string input, basic string, so one is enough. And let's say we call this from Dynamo as a raw description, so we can sort later. We don't put in names. We keeping this field empty. It's not compulsory, and it is quite difficult to handle because the names should be, each name should be unique, and to create this one is a little bit too much for this lecture. And just change the point a little bit. So we want to change the z value of this point because we want to have this later as the peak of our cones. In this case, we want to have a number slider that we hooking in here. Everybody can see this, and we're setting the values from 0 to maybe 20, and in half meters, around 20 centimeter steps. So now we can see that this point moves in Dynamo, but it also moves in Civil 3D. And in order to see it, we need to set the point group as visible in 3D. So let's change the style and make this in model as marker visible. We don't need the. Here it is. And if you move this slider, you can see that this point moves not only in Dynamo, it also moves in in Civil 3D accordingly. So this is basically the first step, what we need for our cone, because the cone in Civil 3D in a thin surface we can't put in as a solid object, so we need to have an approximate thin surface for cones, or for the multiple cones what we saw in the artwork before. So let's create the bottom of the cone, and this is in first thing, it's a circle. And we're creating the circle by center point and radius. And we may want to have also a number slider for this radius. But this circle is not visible, and we also don't want to have it as a circle, we want to have it as a point. So we want to change this circle into points, and that we can do with some nodes from the geometry group under the curves, and there are some general curve, and one of this is creating points on a curve, and that should be point at chord length or point at segment length. It doesn't matter in a circle. So this is our curve, and we're putting this in. No, not a plane. We want to have so our point at equal segment length. That's what we want to have. We don't want to have any plans or coordinate systems yet. And you can see it's already done, and we can put in there an integer slider control the number of the points integer slider. And let's say I want to go a minimum 6 and maybe maximum 90. And I want to have it in steps of 6. So I have 6, 12, 18, 24, and so on. Okay, and I think 24 is a good number that gives us already a good cone. And now this one, we also need to get into CocoaPoints. So let's copy this one. Like layer document, raw description we can keep, and geometry, we see now we have here a list of points because we taught him 24. So we see here 23 points. So let's put them in. And let's have a look. There seems one point on the start and in the end is missing that we add later, but we can see that these points are already in Civil 3D. And we are already able to build a thin surface out of it, but I would recommend that we add first this missing point. And we want to have from the curve the end or the start point. As this is a closed curve, is the same. So let's find the curve. No, curve. Start point. Here it is. Okay, hook in the curve, and you can see the missing point is there. And this one we also need to add to our drawing, and we can see we have every point we need to create one curve. So let's make a surface for this one. Let's call this artwork. This surface. Okay, and we say that this is defined by our CocoaPoints. By point group, add, and we're adding all points. Okay, and here it is. So not that difficult, right? So now we can start to move on with more complex stuff. So what we want to do now is cleaning up a little bit. I think that is first thing what we need. So we don't want to use this CocoaPoint by geometry so often and having so many lines. So in order to resolve this issue, we putting this 3 elements into one list. So let's create a list. And there goes our point for the peak, our start point, and the rest of the points. And now we can delete 2 of these CocoaPoints, and we can use the geometry from this list. Should we flatten this list? Not needed. Okay, and now we just ordering everything a little bit better. So get all the inputs to here. And let's group them. and say this is the input for our cone. That's are the values for the cone. Ah ja, gab's noch. Input cone. And this one, the document stuff, we're moving a little bit all over here. So it doesn't bother us later. And this string we can just put into our input group. And that is the raw description. Just renamed the node because, come on. Okay. And this is actually our output. So make this one, even it's just one node, we're creating a group and calling this output and making this red, or like a red, like this one. So this is quite, you see, this is quite common in for the Dynamo process. And later we're putting this one into a gray node because that shows our computation actually, because we're doing now really computational design. So let's order this one here a little bit. So there are the points. And here are some interim calculation. And that looks much nicer already, the whole graph, and easier to read. Because now we're coming to the next thing. So as we want to have many of them, we need to be able to move them around. And so there would be one logical thing would be to use transpose nodes or move and rotate nodes. But we have actually control over the center point of our circle, the XY of the peak, directly to positioning this this cone. So what we need is now some number inputs that gives us the XY position of our cone. So let's call this one X, accept, and this one we call Y, accept, and this will be the input actually for the position. So we create a group for this and call this group input position. This one doesn't went in, and we add it. Add to group. Okay, and this one we tie in to our peak. You may should give this node also a proper name. Point by coordinates, we know that what it is, but this is our peak. And this is quite clear that we don't need to rename. And let's get in some numbers there to see is there an effect on it. Yeah, it moves the peak, and now we just make sure that we're moving the circle center point. And this is now set to 0, 0, 0. That's our the standard values. So in order to manipulate this one, we need to have a point. That's the input what is required. And we're just using by coordinates. Let's keep it simple. So hook this one in and hook this X and this Y also in. So now the cone is moved in 10 direction, and it should be the same in Civil 3D. So we can see, and it gives us that we need to rebuild our surface, and the cone moved to the place we want. So based on this one, we actually should be able to create now a certain amount of cones in a let's say in an arc or in a let's build an arc. Later we want to have a spiral, but spirals are quite complex, so let's reduce in the first moment the complexity, and then we go later to spiral. So what we want to have is, in this case, a 180-degree arc, and equal maybe every 15 or every 30 degree we want to have one cone. And of course we need a radius. So we don't need XY, we need a radius, we need an angle, and we need a number how many we want to have. And then we need to create this point. And the easiest way to create is using actually polar coordinates. So let's see, can we create a point by cylindrical coordinates? That sounds pretty good. So we're getting a point, and from this point we need to have XY to feed it in later to our other two circles points. So let's get from this point X and Y, because we have Z values different, so we can't hook the point in directly. So we need to have point X and we need to have point Y from this point. And this one replace this XY from our input. Let's move them nicely over here. X, Y, and it was also in there. 2 points, yes. X, Y. And we don't need this one anymore, so we can delete them. So our group disappear. So what we need now is, actually it's telling us, so the why you see now how much sense it makes to work the graph backwards to see what information we need. So we want to have the radius and the elevation values. And no, we don't want to have cylindric coordinates. Sorry, we want to have, yeah, we can use, no, it's fine. So first we need the radius. So we get, again, a number slider. So we can manipulate our radius. This time it's the radius of the spiral or the arc. Number slider, arc. And let's say we want to have it quite big. Let's say we want to have like a 60 meter. And we can see that this already moves a little bit, but the angle is still not there. So let's put in an angle. Let's say 50. The coordinate system we can keep as it is, or we can move it to using the current coordinate system, but it has the current coordinate system a standard value, so we don't need to border, and the z value is also, we don't need to border. So, but we don't want to have only one angle. We want to have actually a sequence of angles or a range of angles. Both works. So let's see what is a sequence. Want to have a start value, the number, how many we want, and what is the increase in each step. So let's put in here for start 0. That we can keep. For the amount, we also want to have just a number. Let's say we want to have 6. And we want to have, for 180 degree, we need an 30 degree angle. And now you can see we have 6 angles from, and that we put in here. And you can see this node know that he has 6 different angles, and the start value is 0. So let's have 7. So we have a half circle of our cones, and we can see how this looks in Civil 3D. There's our hardware. It's there, so it comes already. We get an impression that we can do our nice artwork. So now comes the most difficult part, the spiral. And the spiral has a function we want to use. And now it comes to design script. To creating this function in as visual programming would be a very complex graph with actually what we can actually write very easily as a formula. So let's define a function. And this function gets points at a spiral. And for getting points for creating a spiral, we need to know on which angle it sits, and we want to have, for calculating it as a spiral, it's easier to using radians instead of degrees. We need both on the end, but the more difficult calculation is in radians. And what happened in the function sits in curly brackets. And we know what we want to get back. We actually want to get back a point by coordinates. So the return value is a point by coordinates. So you can see that is actually the same way how we're using these points here. So we're calling it exactly the same way inside design script, like we call it in the visual programming environment. So that's why, as I was explaining on the beginning, that design script is very close to the visual environment, and it gives you an easier and more easy to read way and a more programmer style fashion to create more complex tasks. So, and we're using X, Y, and we know it will be on 0 to our point. So let's calculate X and Y. And here comes now the, so we need an X value. X, and we need a Y value. And we need to calculating, so the formula for spiral is mat is sinus of the angle in degree times radius, and Y is, so the sinus function need to have the angle in degree. So we will convert this to cosinus angle in degree times radius. What is 1e should be enough. Okay, so now we get a radius. The radius on each point of a spiral is defined as an exponential function and by the angle in radians times A times K. Okay, we need to close everything with semicolon. I don't know how to call it in English, sorry. Okay, maybe in every line. Okay, that means we need to get A and K as values into our function. So let's put in A and K. And now what is not defined, the angle in radians comes from the function call. A comes from the function call, K comes from the function call. And what is missing is the angle in degree. Angle in the, here. This is case sensitive actually, so we can't mess it up. Angle in degree is, and there is a function for mat radians mat, and you can see radians to degree is have some kind of, and we put in our angle what comes from our function call. Okay, this is what is he complaining about? Mat radians mat power mat cosinus return point by coordinate xy. Angle degree. I think this is missing here. Let's find the mistake. What is my angle radians mat power mat E angle radians. Here, sorry. Times A, and this goes away. Okay, now our function is correct. It is sometimes a little bit more difficult to write than just lacing nodes together. But if you want to try to make this one as in lacing nodes, you get a huge unreadable graph, or not unreadable, but quite a complex graph. And now we can put in our coordinates back to Cartesian coordinates, because we can, we even don't need this. So we just need to call our function now. And our function is called by points at spiral. And we put in an angle, what we get from this sequence. Let's call this angle alpha. And we need to put in A and K. And we need to close it. And you can see that this code block behaves the same like it would be a normal node. So we can put in now values for A and K, and let's get some reasonable numbers. They are easy to, I know they're giving us a good spiral. So, but we later can change this. You can experiment with this number. So A should be something like 1.125. That is not a valid number. And get a second number. And K should be something like 0.6. What we get, and we need to get, let's start with just with a simple number again. Sorry, now go on. Let's put in a 15-degree angle first. No, we need the angle actually in radians. So let's omit this, and let's create a sequence of angles we want to have. And I already will draw the big spiral. So we have a start angle and an end angle and the number of cones we want to have. So we get a number slider, an integer slider. And the artwork have actually 89. So let's use this one. Let's create our start angle. And again, I'm using a code block because you could write all this with laces and nodes, but it is much easier to using a simple formula. This is our start angle that we want to have later in a number slider times math times P. Sorry, math dot. Actually, we can use P times 2, and the angle and is it's actually the number of windings we are using, how many turns we keep out of the spiral, that the spiral get big enough to getting our cones on it. So we we need the step because we know how many we want to have. So we need to know how many is the winding on the end times mass P times 2 divided by the number of cones we want to have. Okay, there's this one missing. Okay, so we know already this one, and we need to put in some number for this one and a number for this one. And reasonable values are the start winding. So we want to keep out 4.5. I measured it from the original artwork. So and that's why I know these numbers, and I was writing them down, and we have 2.2 3/4 winding. Okay, let's see what we have. We should get now a start angle and then step angle, and from there we can produce now a sequence of all the angles we want to have, angle or XY coordinates on the angle based on the radius. So let's getting the angles first by a sequence. So we have our start value. We know how many we want, and we know what is each step. And we can see we're getting now 89 angles. Let's move all this a little bit to the left. All of them. And this one goes in here to our code block. And we see we're having a couple of points creating the spiral. So we're getting now really close. Now the task is to getting these cones onto the right place. And as we was asking for actually for points. And so we can get actually an X and Y value out of it. So instead of using these coordinates, what we use for the arc, we try just to pull these points into here. Okay, we need to change to manual because now we're having really a lot of COGO points getting updated in Civil 3D, and the tin in Civil 3D is still very weird. So we have a couple of overlapping points, so we don't want to have yet that this getting calculated. But we see already quite nicely that all our cones are on the spiral. They're not on the right size yet. So they don't have the right height and they don't have the right radius because they're getting from inner to the outer walls bigger. So let's solve this one. And then we have almost half, the first half of our spiral done. So this one we don't need anymore because this was just for our half circle. And what we want to have is now that these are changing according to the distance of the center of our spiral. So what we need is actually a distance between this point and this point. And let's see, do we have something like what gives us distances in our nodes? Yes, we have. It's called distance 2. And this, here, where it is? Mirror, input, expert, distance 2. Okay. Now we have it twice. So what distance we want to have? We want to have it from point 0, 0, 0. What is the origin? So let's get the origin point. To each of the center point of the circle. So let's pull the list of the circle, 89 circle, into here. And let's see what we get. Just quickly putting in a watch node. And now we need to start every run manually. And it takes now a little bit longer. That is also a disadvantage of Dynamo, that after a while it gets slower and slower, then you need to restart. But this looks quite good. So we're having now getting all the distances. And what we want to do is making the height and the radius as a function of this value, and that's called mapping. Just let me see. We need now to remap the map. So that is a list function. And we want to remap our range. Is this correct? Yes. So we want to have our distances from the origin. This one we can take away. Or we can calculate actually our distance directly as a function. So let's change this into a code. So this is if it's getting a little bit too crowdy or too messy, then you change it into code automatically. So we're having this function, and this we call distance equal distance to circle 1 and point 1. That looks pretty good. And then we can say that the heights are actually the distance divided by the biggest distance. And the biggest distance is the distance of the last item in our list. And that we call very simple as list last item distance. Because distance is our list of our distances. Okay, and this we we list last item distance. This is correct. And thus we are multiplying with the maximum radius we want to have for our cone. And we're doing actually almost the same for the radii. Sorry, here goes max height. And here goes max radius. Okay, and he's asking for them and we're getting them from here, right? We say this is our maximum height. And this is our maximum radius. And now the center or the radius of each circle comes from here. And the height from each peak comes from here. And before we put it in, so I just disconnect this node here for a moment because I want to do the calculation first only in Dynamo, and later I reconnect this node in order to see it, to create all my COCO points. No, something wrong. Okay, let's figure it out. So it seems, let's move all these nodes a little bit over here so we get a clearer picture. Okay. So we created our points here. We want to have here not this one. We want to have here the radius of our spiral. And I think this we forgot to define. What is the radius of our spiral? Let's put in there a number slider for this one too. And let me remember how much it was. I think I have I think 190, I think. Oh, sorry, we don't need this yet because the spiral is correct. Something is wrong here. This one is correct. Where is this one coming from? We need this point here. And we need point, no, this is here the point origin. And this point is actually the center point of each circle. Circle by center point radius. So we need to have each point from here into there. And let's see. Mhm. Okay, still something not correct. Point. This is here. Each radius is the. That is the. No, this is actually correct. The distance from each. This gives me all the points. Yes, that goes in there, that goes in there. Okay, sorry, here we are. So this is actually the height goes in here, and the X and Y of this one comes from this point. So let's get X and Y from this point. No, not X, one more Y. Okay, let's try to get from this point X and Y, and giving this X and Y to the peak here and to this peak there. Okay, now we're having the peaks correct. Now still the circle is not correct. So the circle get his point from actually also from directly from this point. That is correct. It seems, let's put this quickly radius in to see is this the radius what makes problem. Let's put a radius like 10. Or is it the center point what makes us problem? Okay, so let's have radius is the distance from the maximum distance times maximum radius. Do we have the maximum radius set to 7.4? So we should see actually here a list from 0 to 7.4. Zero to 7.4. That is correct. So this should be the radius of each of our points. Yes. So here we are. And now we're connecting this back to our geometry, our list into the COGO points for AutoCAD or for Civil 3D, and to see how this influence our TeamSurface. Run started, run completed. So we have the COCO points. We may need to rebuild our surface. And here it is. So half of our design is done. So I'm speeding now a little bit up in order to get to the last topic. I think running out a little bit of time. So the next step is to cleaning up this graph and changing the construction of a cone also into a function like we did for the calling the point at the spiral. And then actually duplicating to getting the depression cones and getting the outer perimeter of our design. And as we want to have, I open the final, almost final solution. And that is, no, that's our NURBS solution. This is not our cone 9. Is this correct? Yes. And what is the most important thing? So here, as you can see, it's cleaned up a lot. It's much easier to read and to understand. And what we have now is that I get the position from my Civil 3D drawing. And so in order to do this, we closing Dynamo completely, reopen a new drawing and reopen Dynamo. So Dynamo starts for the new drawing. And this drawing, no, you always can redo this. Okay, it's already done. So let's quickly delete all this. All the COCO points. Yes, I know. Let's delete the combined one. Delete this one because we want to redo this. And we want to delete our artwork because we want to use Dynamo for this one. And we need to delete our grading. That's a corridor, so we need to delete the corridor. Okay. There's a corridor, gone. Okay, and we just making our existing ground visible. And let's say as 216 in the background. Okay. So this is the existing surface. It's actually the adjacent parcel to the original artwork. So I want to place it first somewhere here in the middle. And I know for my design, this is about 190 in diameter, as radius. And in order to place this onto the surface, I just turning on a triangulated style. So let's put on contours and triangles. Apply. Okay. And let's put a big circle onto the surface with 190. And now let's reopen our nice cleaned up Dynamo graph. Of course, you will get all this in the material, and you can see here is one additional part that's selecting an object like we did with the NURBS. It's getting the geometry of the object because it's an AutoCAD object. We need to change it into a Dynamo object, and it's get a circle. And from this circle, we're getting the center, and we're getting the X, Y, Z value of this one, and we're moving our whole list we're not tidying the list directly into our output COCO point node. We're moving it, we're translating it in X, Y, Z direction, all of our points, and then we're getting our out point. Let's try it. Can we do this? So let's get this circle. Let's go back to Dynamo and let's run it. It takes a little bit. Our run is completed. And we have all the necessary points for creating our surface or for our artwork. I left out the center depression that can later everybody do as homework or if interested. And let's create a new surface. Let's call the surface artwork like we did before. And pull all the points in from that we created in Dynamo. All points. Sorry, that is the wrong. That is the wrong. The wrong surface. In this surface, it belongs. Point groups, add all points. Okay. Okay. And let's go to 3D view. And in between, we may jump quickly to the PowerPoint presentation to see where we are. Sharing screen. You share. There's my PowerPoint. So we're doing computational design of landforms, and that's the demo. And what we are doing is we're approximating a form by COCO points of our artwork. We're getting our design area in to putting our design almost to the right point, almost right. We're building all the forms from COCO points, array of points. We're moving them, we array, and now we grading them in a little bit into our existing surface and making a first analysis for cut and fill. So as you can see now, all the points created in Dynamo are into our topographic drawing and in our Civil 3D drawing, and now we can quickly build out of these points our surface for the artwork. And we're calling this simple artwork. And what we need is defining this by point group. And this, in this case, are all points. And here it is. So in 3D view, you see it already with the contour lines, the model is there. So what I want to have is that this sits nicely in the landscape. So I'm grading it in using the edge of my tin model for my artwork as a feature line, and from there I'm grading as a corridor into the existing landscape very quickly and simple. So let's get from this surface the boundary by extracting objects. We need a border, we don't need any contour lines. Okay, here we should have the border now as a 3D polyline. From this one we can create a feature line, and this we give a name because this is the edge of the artwork and it's sitting in the side grading, and let's do it as a basic feature line. That's all good. And now we can create a corridor along this feature line. So we want to have a feature line corridor. We want to get from our side grading the edge of our artwork. We want to get this grading assembly. We want to grade to the existing ground. And let's rebuild the corridor, and we see it's in the wrong direction. So let's get our feature line and change the direction of the feature line. Properties, all three, but I only want to have the actual feature line. And I want to change the direction of the feature line, and the grading sits outside. As this is a corridor, I may need to rebuild this corridor to get this nicely done. So let's combine my artwork with my grading, and then let's check the balancing against the existing surface, because this is the last point in our presentation, is how we creating a complete workflow for an iteration to adjusting our design. So let's quickly create one more surface, create surface that we call artwork with grading. And we just pasting in there to surface. We're putting in our artwork, and we, sorry, that's the wrong surface. Quickly delete because, yeah, okay, yeah, that we know. And let's go into artwork with grading, into the definitions, into the edits, pass surface, artwork, pass surface, grading. Okay. Okay, we don't have the grading surface yet because we forgot to tell that we want to have a corridor from this surface. So let's get a new one. Let's get the topo, and that should be actually and rebuild the corridor. Now we have a surface, and let's change the edits because I want to have the grading first, and the grading should be, because the grading has the middle part, the center part too, that should be overwritten by the artwork. So Let's move this back. So get the grading in first, as this one, and getting also our artwork in. Okay, let's rebuild all this. Let's turn all the other ones off. Don't display them actually. Also the existing ground. No display. Let's have a 3D view to our solution. And let's see it nicely in shaded view. I think we pasted in the wrong direction. Or is there still some? Maybe the grading is maybe still on. That's yes. Okay, and the corridor is on. That we maybe just simple. Let's just simply turn the corridor off. And we see we have what we want to have as form, and it sits somehow okay in the landscape. It's maybe we just check the cut and fill in order to see this more correctly. So let's create a volume surface comparing our design towards the existing surface. One moment, it takes a while. Okay, here we are. So one more surface. In this, we want to get a volume surface. Our base surface is our ground surface, existing ground. And we want to compare this to our artwork with grading. And we call this cut fill. Okay, there it is. And now we can start to optimize this one, this cut fill surface. In order to do this, I would recommend to delete all these points, or at least freeze them to speed up this process. Okay, that was wrong. We turn off the wrong surface. Let's keep it on. And let's go to our volume surface and see what our volume says. And cut fill. And we have a little bit more fill than cut. So we should move everything a little bit down. And therefore, we get our feature line gets represent our edge, and we're doing simple elevation editing. So select all of them. And as we have, well, let me see what was in the dashboard. So we have more fill than cut, so we should move a little bit down. So let's move everything to 25.5. Let's rebuild it. And let's And we're coming closer. So we have now still some fill, so we still can move it down a little bit. And maybe just 20 centimeter. And rebuild, rebuild. And we're coming closer and closer so that we can iterate several variation through. But what is interesting is we have now an area, if you look what is our whole area, where we could move our circle inside this boundary from one corner to the other, maybe at 3 stations, and can repeat this quite quickly. Unfortunately, the generative design, we can't use Refinery yet for Civil 3D. There are several reasons. One is that the inputs possible in Refinery are quite limited to number slider that we could solve by getting some like an XY grid or getting a number of points and using integer to go through these points. And then we can start not only to move, we also could rotate or doing a grading on this circle. But there's a other shortcoming. If you see this changing of a feature line creates a whole change of features in the corridor and the surface. And Visual Dynamo doesn't understand when this calculation is finished. So even I'm able to refresh from Dynamo my surface by command, it's maybe the operation of the regrading is not finished. So as long we don't have a node developed what is able to wait for finishing all the changes coming from the change on the feature line on grading and corridor, and corridor surfaces are all related to this feature line, and only then we can recalculate. But we are able to pull out information from the surfaces, from the volume surface into Civil 3D. We can try. It's also in the Dynamo nodes on my zero touch nodes. So let's go to manage. But it's maybe not in the uploaded yet. Let's get the new one. Does this one already have? No, let's add my no, where is this node? Here. Okay, it doesn't work. Okay, sorry. I will try to, so this will, we need to leave out, but it's possible to read over a zero touch node, over the C# API, the volume of the volume surface. But yeah, it's the interaction between Dynamo and Civil 3D is not that good yet because it is quite new. So we can't automate this process completely yet. But this would be where would be really interesting, how we can have this workflow of moving the our design surface up and down to get really a cut and fill balance. Finally, with a movement of the circle in this area, and then creating about with different slope of the circle himself, about 100 option, and evaluate which one have the lowest cut and fill in all. Not only that we have a balance, we also have the lowest possible amount. And of course, we always can do visibility analysis with 3D views, and it's just some simple lighting. That would be my presentation about the how we can build landforms with Dynamo and bringing them into Civil 3D and manipulating them, optimizing them in Civil 3D. And yes, thank you for your attention and goodbye.